Hello, I'm David, one of the lecturers at the Maths Learning Centre at the Uni of Adelaide. This is Semester 1, 2024, and this is the revision seminar for Differential Equations II. Hello from the past, those watching in the future. Right, that's enough of me staring at not the camera. Okay, so the requests we've had are several, but we've decided we're going to talk about systems of ODEs first. So ODE stands for ordinary differential equation, which means that you have a function and its derivatives in some sort of equation. And the goal is to figure out what the function is. In a system of ODEs, there are several functions that all depend on the same variable, all with several equations that involve those functions. And several equations involving them. I should have brought my copy of Classic so I could look some of these things up. But anyway, yeah, y1, y2, etc. They're functions of x or t or something. All in the same variable, like x, t or x, for example. So when we put y1, it's technically a function of whatever the variable is. But we don't currently know what the formula for that function is, or if we can even find one. But what we do know is we have an equation involving them and the derivatives. So, for example, you might have y1 of t and y2 of t, both functions of time, and maybe they represent, I don't know, concentration of something in a tank. That's the classic. Or they're the populations of two different animals that live in the same environment, for example. Maybe population of two animals, or concentration of chemical in two tanks, or lots of other things, but they're the most common. And the idea is that both of these things are changing with time, but each one is affected by the other one. And so you'll have something like, something like that. It's quite common for them to be presented in the order of, no, this will do. Anyway, we've got two equations there, both of them involving both functions, and neither of them mentioning the actual variable at all, but it's not impossible to have ones that have the variable in them. Possible to have the variable in there. That's also a system of differential equations. But the most common ones in this course are these ones with constant coefficients. But it's not impossible to do it this way. How are we feeling? All right. Now, your only hope of solving them is to have the same number of equations as functions. Because if you don't have enough equations, you won't be able to figure out what the functions are. So you need at least as many equations as unknown functions, which is true for all systems of equations. You need at least as many equations as unknowns. And in this course, they always give you exactly as many equations as unknowns. Okay. There's some caveats there. There's a second derivative here. Then you technically only need one of those, because you can get some extra equations in for free, but we'll deal with that. Yep.
So we're looking for solutions in Y.
Yep, your goal, the goal is to get like y1 equals something involving t, y2 equals something involving t. That's the goal. I mean, the goal of any differential equation is, the function y is equal to something involving t or x or whatever it is. But in this one, we need them both. Okay. And the first step to doing this is to write your equation as all the derivatives on one side equals everything else on the other side. That's the basic way of dealing with it first. So first, y, that's a bold y dashed, which means a vector like y1 dashed, y2 dashed, etc. equals stuff. So you would write it as a vector here. There'd be stuff in each coordinate. That is the first step, to rewrite it like that. Or as a list of separate equations. It doesn't really matter. But the notes will write it as a bold y dashed equals. Probably, if I'm paying attention. Yes. Okay. So that's the first step, because it's easiest to deal with when it's in that format. Because let's be fair, even ordinary one function differential equations are easier to deal with in that format. If it's just y dashed equals some multiple of y, then you know it's e to the power of something. So, okay. So you first rewrite it like that. And so from our example, y1 dashed is 2y1 plus 3y2, y2 dashed plus y2 plus y1. I would rewrite that as y1 dashed is 3y1 plus, sorry, 2y1 plus 3y2, and y2 dashed would be 5y1 minus y2. Not tricky, but it's a thing. Now, if you're lucky, then you will be able to write this part as a matrix times y1 and y2. If not, you're just going to have to leave it that way, because there might be like a y1 squared in there or something. So it is totally possible for this bit here to not have, to not be resolvable into a matrix. But if you can resolve it into a matrix, then you should. So if you're going to use a matrix, if you can, we had this. So the vector y1 dashed, y2 dashed is 2, 3, 5 minus 1 times y1, y2. And most notes write this as y bold dash is a y bold. Something like that. Don't know if your notes do. Yep.
But what if we can find but not in y? Would that then solve?
So if you said t equals,
If every y term had a t term attached to it.
I mean, there's a t, so there was t's in this bit.
Yeah, if you can rewrite it. So basically,
So this one back here could go into a matrix with t's in it. That's what you're thinking?
yeah, solve for t. And we are.
Yeah. That's okay. But like this, like you can't solve for t because it would be in terms of both y1 and y2, and that wouldn't solve the problem. If there was only one function and you could write t equals, then it would be solved. You could undo that and get y equals. Because there's two of them, the t would be in terms of both y1 and y2, which would mean I still wouldn't know anything about y1 or y2, not really. But it is totally possible to rearrange this into a matrix, but it's just got t's in it, which I don't know how to deal with. That's not in the course. So it is also possible if there's like an extra bit here that has just all the t's are in this plus here, then you can put them in a vector of their own.
Yeah.
Yeah. So it is possible to have like a plus something involving t plus something involving t and have like an extra vector here with the t's in it. That's possible, and there are ways of dealing with that which are very similar to Euler's method. Like numerical ways of dealing with that, or MATLAB ways of dealing with that, which are numerical ways. In past courses, students have been asked to rewrite it that way. Oh yeah, they'll be like an RT. So I'm just going to have, damn it, damn. I'm going to do this other one as well. So if it's linear at all, then you can still rearrange it into y1 dashed equals and y2 dashed equals. So that would be like 5t y1 minus y2, and then I have to divide by t squared. Like that. And then I can get y1 dash y2 dashed equals 1y1 and ty2s and 5 on ty1s and minus 1 on t squared y2s. And there's an extra t squared 0 left over. That's totally possible, and is a thing. And there are ways of dealing with this numerically, but you've only been taught how to deal with it when this is 0 and these are all numbers. But you have been taught that this is a thing you can do if you wanted to. Yeah. And it is possible that you can't separate this into a matrix and you just have to leave it as a big vector that's got t's and y1s and y2s in it. In the notes, they call capital F y1 up, yeah, anyway, up and t. So mostly this is possible to write, but course only shows how to solve, and this is constants, and this is 0. Okay. All right. Cool. Once you do have it, so far, just where are we? Damn it. You can see how it works when David's making it up off the top of his head. So once you're in, so we had our original system. I'm just going to start from scratch again, just to remind us where we were. Y1 dashed is 2y1 plus 3y2, y2 dashed plus y2, 5y1. And then we converted that into y1 . And then we converted that into y1 And we converted that into that. Once it is in that format, then you can use eigenvalue and eigenvector methods to solve it. And it is a magic trick. And the magic trick goes like this. As all the magic tricks in differential equations go, I'm going to hope that the answer is in a certain format and run. So usually, if a derivative was a multiple of the original function would be e to the power of something. Those are the only functions whose first derivative is a multiple of themselves are e to the power of something or just a plain constant. Because a plain constant, its derivative is 0 times itself. But things that aren't plain constants are e to the power of something. So I'm going to assume that the solution is some number times e to the power of lambda t and some other number times e to the power of lambda t. That y1 is something times e to the lambda t, and y2 is also something times e to the power of lambda t, but possibly a different something. So I'm going to suppose that y1, y2 is some vector times e to the lambda t. I mean, officially it's e to the lambda t in front of the vector, but it's okay. I'm allowed to put it on the other side for my own purposes. Yep.
And the t, when you multiply through by t, also applies.
Oh yeah, there'll be a whole thing, but yep. But this is the beginning supposal, and we may have to fix it later. May have to fix that later by multiplying by t, like you said. And this v is constants. That's important. So if you do suppose that, it turns out that the v ends up being an eigenvector for your matrix, and the lambda ends up being an eigenvalue. Because when you differentiate this with respect to t, you get... So this is, you don't have to show this all the time, but just watching it, you'll get that y1 dashed, y2 dashed. The v, if you differentiate each coordinate separately, the v will still be there because they're both constants, and you'll still have the lambda t, and there'll be a lambda that will come down. And so what you'll end up with is lambda v e to the lambda t is equal to matrix A times v e to the lambda t. So this is the matrix A. This is v e to the lambda t. This is lambda v e to the lambda t. And e to the lambda t is 0, is never 0, so you can divide by it. And you get lambda v is AV, which is an eigenvector eigenvalue equation. Yep. But if it isn't, but if it turns out that doesn't work, we can fix it later. So it turns out that even if the solution isn't e to the lambda t, we can start here. And all of your differential equation solving methods, almost all of them are, suppose the answer looks like this, sub it in and see what happens. And today, when we sub it in and see what happens, we get eigenvector eigenvalue equations. How do you feel about what happened there? So what most people do is that they usually skip this working and go straight to there, because yeah, unless you're explicitly told to prove that it works, you can just do it. But other people who can't remember what to do can remember, like, you have to remember what format it is in order to use your answer at the end. So if that's the only thing you can remember, you can always figure it out from here. So now you have to find the eigenvalues and eigenvectors of this matrix. If this had 3 functions and 3 equations, you would get a 3 by 3 matrix, and it would be just that little bit harder to find the eigenvalues and eigenvectors, or at least a little longer. How are we feeling? So we have to find the eigenvalues and eigenvectors. And to find the eigenvalues of something, you have to solve the determinant of that is 0. That will find the eigenvalues. And then for each lambda, you'll solve lambda I minus a, v equals 0, and v equals will be the vectors. Okay. And it is a linear differential equation, so as long as you find two solutions, all the rest of them will be a linear combination of those. And so that'll be fine. Or 3 if it was a 3 by 3 matrix. So, okay. So, lambda minus. So we're going to minus the 2 and a minus 3 and a minus 5 and a minus 1. That's what lambda I minus a is. And the determinant of lambda I minus a is lambda minus 2, lambda plus 1, minus 15. I really should have actually chosen numbers that worked out to something good at the beginning, but here we are. I have choices. I can expand it out and use the quadratic formula, which is probably the easiest way. I could attempt to complete the rectangle or square if I was concentrating really hard. I'm just going to do that because I'm not in an exam. I'm going to go halfway between these two, which is at, when I add those two, I get minus 1, so minus a half. Is that okay? So halfway between them is minus a half, and minus a half minus 1.5 is minus 2, and minus a half plus 1.5 is 1. Fun, huh? This was not a good plan, but anyway. Yeah, it's going to be bad. Yep. And so that's supposed to be 0, and so lambda minus a half squared is 16 on 4, 69 on 4. And so lambda minus a half is root 69 on 2, and lambda is a half, well, plus or minus is a half plus or minus root 69 on 2. Yay. My high school textbook writers would be mortified that there's a 69 in there. The Desmos textbook writers actually have a person whose job it is to make sure that there are no examples that have either answers or questions involving 69 or 420. Well, that's not their only job, but they have a week that is their job. Anyway, but here we are. I did a bad job of choosing my eigenvalues, but at least those two eigenvalues are real and different. And so I will get, I will have to figure out my eigenvectors that go with them. Curses. But there will be, each of them will have its own separate eigenvector to go with it because they're real and different. Real. Yeah, I'd have to change the original matrix, but yeah. Real and distinct. And so my answer is going to be like V1 e to the half plus root 69 on 2t, and V2 e to the half minus root 69 on 2t. They are the two answers, and then all the answers will be like C1 times this plus C2 times this.
Saying that we would work before, but of course we tried.
I don't know. No. Only constant coefficient. Or at least, I'm sure there are ways, but this is the way that is in your notes. So that's sad, and I may change my matrix to get certain eigenvalues that I know. I'm just going to give you a simpler example if that's okay, because I do not care to sub either of these back into here and attempt to solve it for the eigenvalue vectors today. So let me try another one. What was my matrix? 2, 3. All right, that matrix. I've changed one number in my matrix. I've changed this number. So that now 5 is one of the eigenvalues. And the other one is necessarily -4. So dot, 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 lambda equals 5 and -4. Yes, definitely 5. And yeah. Well, if I knew one of them was 5, then the other eigenvalue would have to, like the sum of these two has to be the same as the sum of the eigenvalues. And so if one of them is 5 and these two add up to 1, the other one has to be -4. So, so thank you. Here we are. So I'm just, the dot dot is the working that we've just done before. I'm going to skip that if that's okay. But I do still need to, so when lambda is 5, I'm still going to need to do the lambda I minus a and solve that. So it'll be 5i minus a. And so I'll have 5 minus 2 is 3 and a 3 and a -3 and a -6 and 5 minus -1, which is a 6. And officially I'm solving this equation. Like 5 minus a v, damn me. Five I minus a v equals 0. And this row is a multiple of that row, so I can subtract the appropriate multiple and make it zeros, and I can divide this one by 3, and I'll get this. Produce this. So if you're absolutely certain that the row operations will get there, you don't have to show them. But if you're not sure, then do them properly so that you don't lose any minus signs. But that row is a multiple of this row, so it definitely becomes 0. And I divide that one by 3, and I got to here. And then there's a pivot there, so there's a free variable here. I've already used t as the variable that the functions are a function of, so I might use s. And so I'll make this one s, and then I'll have 1 x1 minus s x2 equals 0, so this will be also s. So it's, yeah, one of these minus 1s equals 0, so one of these must be also s.
So that means that if I make that solve the equation, it's sort of not the same as like something like
Correct. And officially, that's what causes the C1s and the C2s. It's this variable here. That's there. So, and so you just pick whichever multiple of this you like, and 1, 1 is a perfectly good multiple. And then we'd have to do lambda equals -4 and solve -4i minus a v. And the nice thing is that if I had written down on my page this thing, I could sub it into that, which makes it a little easier than trying to do it in your head the whole way. But -4 minus 2 is -6. -3 -6, and -4 minus -1 is -3. And if it really is an eigenvalue, this will happen. You will, if it's a 2 by 2 matrix, if it really is an eigenvalue, one row has to be a multiple of the other. There's no way around it. And so I can maybe divide everything by -3 and I'll get something like this. And I'll make that my pivot and make this one free so that this is -2s, like that. And so I've got that my v here is s times 1 minus 2. And just to check that that really is an eigenvector, this times 1 minus 2, oh, I can't fit them both on the screen at the same time. Do a fold in. 2 minus 6 is -4, and 6 plus 2 is 8. And so that is what I get if I multiply both of them by -4. So it really is an eigenvector that goes with -4. So you can always check eigenvectors. Yes?
That are the free variable and it's in the form of v, e, quantity.
Yeah.
Now where v has the free variable.
Yeah. So two solutions. I can do it this way. One of the solutions is 1 e to the 5t, because that was the eigenvalue that went with this eigenvector. And another solution is 1 -2 e to the -4t, because this one went with -4. And then all the solutions, like the general solution, is that y1, y2 will be something times this. No. Because the whole point of this was to get rid of the dashes. Ta-da. And if you were very lucky, you would be given some initial conditions that would allow you to figure out what the A and the B are.
Or you can write them as two distinct solutions.
Yeah, you could write y1 is A e to the 5t plus B e to the -4t, and y2 is A e to the 5t minus 2b e to the -4t. So I've used the first row and the second row. And you can check it at this point if you really had time. I never had time to do this in an exam, but I always worked all the way up to the end. But you can now, if you really want to, differentiate this and see if it comes to the same answer as what you get when you multiply by that matrix. You can do that. So just to check, I'm going to do it. y1 dashed is 5a e to the 5t minus 4b e to the -4t, and y2 dashed is 5a e to the 5t plus 8b e to the -4t. But if I did 2, 3, 6 minus 1 times a e to the 5t plus b e to the -4t, I'll get 2 of, that's all one number, right? 2 of that plus 3 of that. So 2 of that plus 3 of that would be 5a e to the 5t, and 2 of that and 3 of that would be 2 minus 6, so -4 e to the -4t. That's good. 6 of that minus 1 of that is 5a e to the 5t, and 6 of that plus 2 of that would be h e to the, sorry, I've missed the b, e to the -4t, and it's working out the way it should. Yay! Of course, I've never had time to check in an exam, but I did check my eigenvector as I went along. So at least I was sure of that. And that's much easier to do than this. Yep. So we should do one of those, hey?
what the words for ODEs that have the same parameter to
Yeah. Have the same independent variable. I think that's what it's called. In my head, it's an input variable, but yeah, so the thing is that that's all well and good, but what if you have complex solutions or you didn't get enough eigenvectors for your eigenvalue? So there's some things that can happen. We should do some what ifs. What if you're in like a 3x3 situation, for example, something like that, and you got your eigenvectors. What if when you got lambda equals 3, you got v is like s of vector plus r of vector, right? Just going to make up some crap. What if you got that? Oh, there'd be 3 coordinates, wouldn't there? 3 coordinates. I'm really hoping this isn't a combination of those because that would be bad. What if you got that? Well, that's okay because you've got 2 completely different vectors that go with 3, so you'll just have them both. You'll have your final solution for y will be something times 1/2 0 e to the 3t and something times -651 e to the 3t and something times -205 e to the 2t. So if you get 2 different eigenvectors, they're the same eigenvalue, that's okay. Just put them both in with each with a different constant. Yeah, that's right. 2 different bases. And it is, you're looking at this and going, well, why can't I add them together and have that many e to the 3t's? Well, you can't because you might have a different number in each of these, and the coordination of the 2 different coordinates gives you a different answer for what y2 and y3 are. Yeah. So that's a what if. What if you got lambda equals 3, 3, 2, and for lambda equals 3, you only got 1 vector. Apparently not. There is a multiplying by t involved. So I'm just going to read this theorem, theorem 2.10. 2.10 to the rescue. It says, suppose lambda is an eigenvalue of A, a multiplicity 2, but with only one independent eigenvector called x. Then in turn, blah, 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 blah. So you'll still have the v e to the lambda t for this one. And then the other one will be times by t, but also another bit, an extra bit. Okay. Yeah. Oh, well, I don't know. Please don't worry about it if it's not there, but there is a theorem. I'm just going to say theorem 2.1 to the rescue. It's the same process that finds the Jordan basis vectors in algebra 2. Curses. So if you do algebra 2, that might make sense to you, but if not, then don't worry about it. But yeah, the theorem 2.10 is the thing that's to the rescue. If you don't remember it, and therefore it wasn't important enough to be assessed in one of your assignments, it's probably not in the exam. Yeah, but it is possible to find a second vector to go with this one, and to use that and an extra t to solve your problem. But you're right, in an ordinary DE situation when you only have one equation and one function, if you get a number that's comes out from your, if you get a number that comes out from your lambdas and it's there twice, you just multiply the other one by t. But with this one, because they're vectors, you have to multiply by t and then add an secret extra vector. Sorry, everybody. Called a generalized eigenvector, which you figure out from the one you've already got. So the actual rule is what you'll do is then you'll solve lambda I minus a times v equals the v that you already got. And you use that vector. You'll use that vector to construct a new solution. Yeah. Curses. And there'll be more stuff. But that is theorem 2.1. Just want to say that it's a thing. But if you don't remember it, which means it wasn't in an assignment, I wouldn't expect it to be an exam. But of course, battery's not included. I don't know what's a new exam. So I don't know what sort of psychopaths you have as lecturers. So if it's trenched, it's probably pretty frank. So yeah. If it was Tony Roberts back in the day, you never know. Yeah, and it's on the recording now. Oh well. Sorry, Tony. Okay. All right. What if it turned out to be a complex one? So what if you got something like that? I choose not to try and think of the matrix that produces that answer. Yeah. So if that is the case, then we're going to perform another magic trick. So we do know for sure that, damn it, I'm going to need to do it. I'm sorry. It's really important to be able to do this. So I'm just going to have to do a little scrawling to figure out a matrix that has complex eigen things. I'll make one up. I'm going to do a small one, a 2 by 2. Yeah, let's do this one. That matrix. No, not that matrix. What am I doing? Bear with me. That matrix. Okay. You can see what's going to happen. There'll be squares everywhere. But so I'll get my lambda I minus a. And so my determinant of lambda I minus a is going to be lambda minus 2 squared plus 9. Because it'll be minus 9. And that's supposed to be 0. And so I've got lambda minus 2 squared is minus 9. And so therefore lambda minus 2 is plus or minus 3i, because of the negative number produces the I when we square root it. And so lambda is 2 plus or minus 3i. Okay. Sweet. So then what I need to do is I need to find the eigenvector that goes with one of those eigenvalues. And the first magic trick is that I only need one of them. I don't need to do both of them. because if you have an eigenvalue that is complex and a real matrix, then the eigenvector that goes with the conjugate will be the conjugate of the eigenvector that goes with the original. If you conjugate the eigenvalue, then you conjugate the eigenvector as well. And so you only need one of them because the other one will be the conjugate. So pick one. I choose the plus. And so I need to choose, I need to solve this. And so that will give me lambda minus 2. So 2 plus 3i minus 2, which is 3i. And 2 plus 3i minus 2, which is also 3i. I have to solve that. Now, if this really is an eigenvalue, then these two rows are multiples of each other. And you see, this row must be I times that row because of that. This is 3 and this is 3i. This row must be I times that row. And let's just check I times that is indeed minus 3. So row 2 really is I times row 1. It's worth noting that I've chosen one that was particularly simple and doesn't always work out that simply, but you can always check to see if you've done it right by finding out what this one row multiplied by another is to produce one of the things and doing the other one as well. So it should always work out that way. So I know that I can do row 2 is row 2 minus I of row 1, and it will work. Just to be absolutely clear to myself and the person reading it that I really did the work. And then I'll do row 1 is row 1 minus divided by 3. So I've got I and 1 and 0, 0. But if you trust yourself, if you trust this working, you can just assume that one row is a multiple of another. If it's a 2 by 2 matrix, if it's a 3 by 3 matrix, all bets are off, and you've got to do the row operations with the i's in them. They're both going to be complex, but yeah. Anyway, that's my pivot there with the 1, 0. And so this one, so I call that S, and this would be minus I S, because it's always minus what's in that spot. And so my vector is this. And the eigenvector that goes with 2 minus 3i will be I1. It'll be the conjugate of this. But I care not, because here is the second magic trick. Okay, so one of my solutions is definitely this. Is that. Like that. Is that okay? E to the 3it is cos 3t I sine 3t. I'm just going to leave that e to the 2t out the front. So this times minus I will be minus I times cos 3t. And minus I times I is 1. This minus I squared would be minus 1, which is plus 1. And this is 1 times cos 3t. So yes, you are right. Usually one coordinate has a real number and the other one has a complex number. So if this was minus I plus 1, this calculation would be a bit more complicated. You'd have 4 things to multiply. Okay. Yep.
Okay, just like to the part where you throw away the real part of it. Like signing that.
I factored out the two. This is 2t here. I did not do that. I said here that x2 is equal to t. Here. Oh no, it just had it lambda minus 2, so it took away the 2. Like when I sub this into there, it says lambda minus 2, so 2 plus 3i minus 2 is just 3i. So yes, I'm sorry for choosing the example that made it look like you just throw away the real part. You don't do that. You sub it in here and see what happens. Sometimes that would be lambda minus 1. We'd still be left with a 1 plus 3i. So just be careful. Beware of the toast. Don't follow the pattern. Reason. Okay. You know what beware of the toast means, right? It means don't follow the pattern. Reason. The human brain is really good at following patterns, which is why we're so good at learning things without even knowing we're learning them. And that's why lecturers should provide several examples so that you can figure out what the pattern is, but you should always reason it out just in case things are a coincidence. Okay. But it's also why people won't eat nachos if on the same day they threw up. Like in the future, they'll go, oh, those things are connected. That is your mammal survival system. Okay, so, and we are nearly there. So we have this real number times all of this. So the second magic trick is that I can form from, I know the other solution that goes with the other eigenvalue is the conjugate of this. And I know that if I have a complex number and its conjugate, if I add them together, I get the real part. If I have a complex number and its conjugate, if I subtract them, I'll get minus the imaginary part. And so I can make the real part and the imaginary part of this vector out of the two vectors that I know are part of the solution. And so all I have to do to get two real solutions is take the real part and the imaginary part of this. So the real part, the e to the 2t is multiplied by everything, so it'll still be in the real part. And the real part is this, sine 3t cos 3t. And the imaginary part is this, minus cos 3t sine 3t. So you remove the I, you're just saying the coefficient of I. And these are the two real solutions that we have made. And we only needed 2 because it was a 2 by 2 matrix. And so now we can say that y1, y2 is something times this one plus something times this one. Magic trick. Complex numbers are magical, frustrating in some ways, but produce some cool stuff in other ways. So in general, if you have complex number solutions, you will get sines and coses. There's some sort of rotational thing going on here if you get complex number solutions. A matrix with no real eigenvalues has to be a rotation. And it's all connected because it has to be. This is maths. Yeah. So if you're in a 3 by 3 situation and there was yet another eigenvalue, you would just do its thing with that one separately. Yeah. I mean, if you've got a 3 by 3 matrix that's got real entries, you have to have a real eigenvalue. It's impossible to do it any other way. Yeah. So with the one real, you do it the way you normally do it. And with the two complex ones, you'll do this. Yeah, let's do the series. Unless there's anything else about systems. I can go over time at the end as well. So if I need to. Well, I mean, you can leave, but I'll keep going. Cool. There is one last thing, is that you can turn one second order ODE into a matrix system if you want, by doing a magic trick. So I should probably just mention that while I'm here. So you could, for example, you turn a homogeneous ODE of any degree with constant coefficients into a matrix, if you want, by doing this. Y1 is going to be Y, and then Y2 is going to be Y dashed, and Y3 is going to be Y double dashed. And what that means is that Y triple dashed, Y3 dashed is Y triple dashed. So you make the first three derivatives their own functions, and then the very last derivative is the derivative of the previous one. That's how you do it. And so then the equation becomes three Y3 dashed minus 2Y3 plus 5Y2 minus 6Y1 equals 0. And so you get this system. And the system is made of this one, this one, this one, and this one. Yep. Yeah, because there's only one equation to begin with. And so you end up with Y1 dashed is Y2, which is here. And Y2 dashed, oh crap, that we can do this here, just a second. This is also equal to Y2 dashed here. And this is also equal to Y1 dashed. Crap, I was wrong, I had a little bit. So Y dashed is also Y1 dashed, because Y is Y1. And Y2, Y double dashed is Y2 dashed, because this is already Y dashed. So we were doing that all along, sorry about that. So Y2 dashed is Y3, and Y3 dashed is 2/3 of Y3 minus 5/3 of Y2 minus 2Y1, rearranging this equation here. And so there it is. It's a perfectly good system of linear differential equations. And so I have that Y1 dashed, Y2 dashed, Y3 dashed is 0, 1, 0, 0, 0, 1, minus 2, minus 5/3, 2/3, Y1, Y2, Y3. And you can find the eigenvalues and stuff, but then you're only interested in the first coordinate of all of those at the end, because you only really want to know what Y1 is. Yeah. Only you really wouldn't do that. You'd just put a lambda in, right? Like you'd just go lambda cubed minus 2 lambda squared, like 3 lambda cubed minus 2 lambda squared plus 5 lambda minus 6 equals 0. Solve that, find the eigenvalues, do your real and complex or whatever. But the idea is that the reason that other thing works and the reason we use lambda is because it really is an eigenvector, an eigenvalue. So it all turns out the same in the end. You end up with, what you end up with is that when you do the characteristic equation, so at the very end, I'm going to put it in a box. At the very end, you end up with the characteristic equation of that matrix ending up being 3 lambda cubed minus 2 lambda squared plus 5 lambda minus 6 equals 0. Yeah, which is just a fabulous magic trick. So, and that's why we use lambda, because it really is an eigenvalue. So some lecturers think it's really important for you to be able to do this process of turning it into a matrix. Some lecturers just are okay with you knowing in yourself that it is there, but not having to do it. Right. You okay with that? So if I was concentrating, I would have done even, it's not, it's actually this, that's the equation we want. Yeah. That's what produced these. Okay. It's done now. Done. Oh, all right. Okay. So one of the things that functions have is Taylor series. Most of them do. Well, that's probably not true. If you talk to a proper analyst, like analyst, I don't know what you call them. You talk to a proper a mathematician who studies analysis, they will tell you that most functions don't have Taylor series. It's just that most of the functions that we're capable of writing formulas down for do have Taylor series. So functions have Taylor series. And maybe if you didn't know what a function was, maybe one of the ways to get at it would be by finding its Taylor series first and working backwards to find your function. Maybe. Okay, that's the idea. And maybe even if we couldn't work backwards to figure out what the function actually was, maybe we wouldn't care, because most functions are quite close to their Taylor series, even if you only use a few terms. Yeah, assuming some technical details from your from the theorem, and most functions are quite close to the first few terms of their Taylor series, especially if the variables, the independent variable is only up to 1. Between 0 and 1. So this is the only reason I have thought for why non-dimensionalization is a good idea, because it tends to have the outcome that your variables, the values of your variables are between 0 and 1. So when you non-dimensionalize stuff, you divide by, the maximum or the total or something. You go, oh, I've got a rod that's like that's L meters long. and I'll divide by L, and then the L will be gone. And now it'll be between 0 and 1. And that's nice because Taylor series are really useful for functions that are between 0 and 1. Because a Taylor series will have something like right? And if x is a number between 0 and 1, then x cubed is even smaller. And x4 is even smaller. And so for numbers that are less than 1, the successive powers get smaller and smaller and smaller, and therefore become less and less important. So, yeah. So, maybe I have a chance of having an idea of what my function is, or at the very least knowing what the first several terms of its Taylor series is, because that might be good enough for the purpose that I'm working for. And so I'm going to wonder if this is an expression for the Taylor series, what are A0 and A1 and A2 and A3 and so on? That's the question. And that's why we use series methods. Series methods are especially and wonderfully useful for things that have polynomials in these spots. Polynomial here, polynomial here, polynomial here, like that. That is not the right for. Useful for things like this. If you have a polynomial as the coefficient of your various derivatives of y, then this is kind of a polynomial as well. And when you multiply polynomials together, you just get more polynomials. And so if your differential equation is in this format, then a power series method might help. But if I had like an e to the x here, it's not going to help. So you ask why you would do it. Two reasons is because Taylor series are useful generally. Second reason is that polynomials in these positions, or numbers in those positions, are great. Because that will be amenable to doing the sum notation that we want to do. Did you have any thoughts to add? I'm not upset at you. I just really wanted to know if something that you were thinking would be useful for us to know. Okay, so there are some famous differential equations that are in this format. There's Euler-Cauchy and Bessel's equation is one of them. And there's another one, Legendre's equation. They're the three famous differential equations that are in this format. Euler and Cauchy's equation doesn't require an entire series. It only requires one term to solve the problem. But Bessel's equation and Legendre's equation are more general. Okay. But it's not that Bessel's equation, it's not that all equations that this is useful for are called Bessel's equation. It's the other way around. Bessel's equation is a very special kind of this thing. And this will be useful for this process will be useful for anything that looks like this. So, more or less work depending on how many polynomials are actually there rather than just constants. No. The polynomials are the way they are. We're going to express y as a Taylor series. I'm going to show you an example, but you express y as a Taylor series, and then you sub that in here, and when you multiply a Taylor series by a polynomial, it just produces more series. So it all hinges on polynomial times series equals several series. That's what it hinges on. So my example goes like this. I'm just going to make one up. It will probably turn to utter shit as I go. I'm sorry. But the if we can do this one, we can do anything. Here it is, x squared plus 1 y double dashed minus 3x y dashed plus 4 plus x y equals 0. Only works, this process, for homogeneous ones. You need an equal to 0. So, sorry? The series method works for homogeneous differential equations. Correct. And I repeat that, if it wasn't homogeneous, you would solve the homogeneous one first, which you would use with series, and then you could do whatever other methods find particular solutions. Yep, variation parameters or undetermined coefficients, depending on how easy it was to do. Yep. Okay, so the way you do is you suppose that y does in fact have a Taylor series. Which is this. I think your lecturer probably uses M. It doesn't matter what letter you use. Now, you're only allowed to do this if, when you put this in standard form by making the coefficient of y double dashed 1, there's no zeros and the denominator is not 0 when x is 0. So it's not allowed to have 0 as a singular point when you do this. That's a technical detail. Just check minus 3x over x squared plus 1 and 4 plus x over x squared plus 1. Both analytic at x equals 0, so it's okay. So that's just a little aside. You're supposed to check that. And if they weren't analytic, then you'd use Frobenius system. If you were lucky. And if you weren't lucky, you would just stop and go, no, not my problem. Or, you know, design a whole new mathematical theory or something, I don't know. So that's okay. That's why I deliberately made this not x squared. Okay, so you're going to suppose that. And you're going to sub this in there and see what happens. So the AM is a constant multiplied on, so it's still there. I reduce the power by 1 and multiply by the existing exponent and make this one go down by 1. You get to decide if you make that a 1 there, because technically the constant term, this one vanishes. And so, and if m is 0, this is 0, right? It's up to you, I'm pretty sure. I think the lecturer made it a 1. But whatever. Makes me feel better to do that. Because there's not really an x to the negative 1 in this. That's anyway. And if I differentiate it again, I'll get this. And now I will sub all of this into here. And what I'm going to do is I'm going to sub all of this into each part separately instead of the entire equation, because there's just so much happening here and it's just going to go forever before I get my equals 0. So I'm just going to sub it into each part. And what I'm actually going to do is even more. I'm going to go x squared times y double dashed and 1 times y double dashed and 4 times y and x times y. I'm going to do all of them separately. So I've got 5 things to do. So x squared times y double dashed is if I multiply by x squared, all these exponents will go up by 2. That. Because the m minus 2 times x squared, x to the power of n minus 2 times x squared, you'll add the exponents and you'll get an m. And 1 times y double dash. Oh, wait. I'm just going to leave a gap because I might have to do something later. 1 times y double dashed is exactly what it was, but I know that I've already written it down, but I just need to keep my bookkeeping in order. And minus 3x times y dashed. Where's y dashed? Minus 3 am x to the m. Because I multiplied by x, so this has gone up by 1. Okay. And 4y, I don't need to look that up. And x times y, damn it. These are all my pieces. Can't even see them all at once, but there they are. All my bits. And I know that the total of all these things is 0. Because that's what my equation says. That is part of the goal, yes. So, in fact, the goal is to make an expression officially that has x to the power of m. And then you can say, well, if this function, when I add this all together, I get this single function, and that function is equal to 0 no matter what x is. So we're saying that no matter what value of x I sub into whatever the function y is, because y is a function of x, no matter what value of x I sub in, it always comes out to 0 no matter what. And the only function that is a Taylor series that always comes out to 0 no matter what is the one that has 0 for every one of these coefficients. And so what I'm going to do is equate all the coefficients to 0, and that should allow me to figure out what the a's are. So the only way to equate the coefficients to 0 is for all the coefficients to match. I have an m and an m minus 2 and an m and an m and an m plus 1. I should be able to move my m minus 2 forward to make it in terms of m, and my m plus 1 back to make it in terms of m. And that would that'd be good. But if I had had a whole lot of m plus 1s and only one m, I would have moved that one to match the m plus 1. It doesn't really matter what direction you move them, shift them. I would choose whichever of them makes the least amount of work. So some people prefer to make everything m. It just makes them, it's easier for them to process. I prefer to just move as few as possible. So, and I didn't know which ones I would move until I got to the end. And so I can see I've got this and all of these. I'm going to move that one and that one. So I'm going to shift the indexes. That's what this process is called. I want this to be an m, which means I need to add 2 to all the m's here. M plus 2 minus 1 is m plus 1. So I added 2 to all the m's there. And so that I haven't really changed the expression, I have to subtract 2 from all of these m's. Because if I add 2 and subtract 2, I haven't really done anything. Like that. So I added 2 here to all of those m's. And then in order to compensate for that change, I subtracted 2 from all of these m's. So it all evens out in the end and comes to the same answer it was before. That is index shifting. And it's totally okay to have a -2 here, because at no point do I actually have really an x to the power of -2, because that's when I sub in -2 into here, it's a 0. So that's all good. Everything's fine. And this one I'm going to shift, but this time I'm going to bring them down. I'll have to subtract 1 from all of these m's and add 1 to these m's. And now all the xm's match up. So I'm now using this and this and this and this and this. There's 5 of them, and I add them all together and I get 0 for every coefficient. So you could, if you wanted to, write down something on the page at this point. It's not actually necessary. Say the total equals 0. So you will equate the coefficients. And so the earliest m that appears anywhere in these is -2. Make available across all of these. The earliest m that appears in any of these things is -2. I'm just going to keep going. Like the place where the recurrence relation starts is the last m that appears in all of them. Like the first m that appears in all of them. So sometimes, yeah. But this one, that m equals -2, that doesn't really count because it doesn't exist. This is 0 actually. And when m is -1, this is also doesn't exist. So you can make that an m equals 0 if you want.
You have to get all this information.
No, you don't need to make these match, but it's useful to think about whether they do. So you'll notice that actually this one doesn't really start until 0. Technically, this one doesn't start till 1 because it's 0 when m is 1. And this one doesn't start till 1 because it just doesn't start till 1. It turns out that the recurrence relation doesn't start till m equals 1 because that's the first m that's in all of them. And so you may have to have a separate equation for what happens when m is 0. That's what I'm saying. So it's in all the terms. So it will need its own equation. And so when m equals 0, I get a0. So the coefficient of x to the 0 is a0 times 0. So that's okay. And this, this one actually starts at 2, actually. Anyway, I don't need to worry about that. I can deal with it as I go. Actually, this one starts at 2, so the recurrence relation only starts at 2, actually. Whatever. It probably doesn't matter. I'm just going to leave it as it is. This was -2, was it? So theoretically, I should start at -2, but -2 doesn't actually exist, right? But if I was going to be really systematic about it, m equals -2 doesn't occur in all the terms. And when m is -2, this is the only one that has a -2, and I get a0 times 0 equals 0, which is fine. And then when m equals -1, that looks like a plus. That's not in all the terms, but that's also only in this one, and that gives you a1 times 0 equals 0, which is fine. And when m is 0, I've got more of them, right? I've got a0 times 0 from this one, and a2 times 2 times 1. That's a thing. And this one has a minus 3. No, that's A0 times 0. This one has a 4 A0. And this one has an A negative 1. Well, no, that one doesn't have an A0 in it. So an M equals 0, so don't worry about that one. And so I get that 2A2 plus 4A0 equals 0. And so A2 is minus 2A0. And now from M is greater than or equal to 1, that does appear in all terms. That's in all of the sums. All of the sums have M equals 1 in them, and therefore they have M equals 2 and M equals 3 and whatever, because they all go to infinity. So now this is when the recurrence relation happens. So I can just go AM, M, M minus 1. And AM plus 2, M plus 2, M plus 1, and minus 3 AM times M, and plus 4 AM, and then plus AM minus 1. And all of that is supposed to be 0. And you can rearrange this to get the latest M equals everything else. So I'm going to do AM plus 2 equals everything else. And that's the recurrence relation. Yep. I'm going to repeat that question and answer it. So I mentioned if I didn't get something, I'd use Frobenius. So at this point, you would normally start figuring out like I know what A2 is in terms of A0, and then I would start figuring out each of the later ones in terms of the earlier ones. And possibly A1 as well. Probably. Yes, I reckon. This one's going to be interesting because it's got an M plus 2 is based on M and M minus 1. Yeah. So we know what A2 is in terms of A0. And each one is made of not the one before, but the two that are even earlier than that. And so A1 can't be made, but A3 can, because it will be made of A1 and A0. And so this one's quite uncommon because based on the ones that they've given you, because we've got that AM will be involving AM plus 2 will be involving AM and AM minus 1. And so you can, if M was 1, A3 would be based on A1 and A0. And so there will be an A1, there's no way to figure that out. And so you'll have an expression at the end that's based on A0 and A1. Yeah, and they will, determined by initial / boundary conditions. Yeah, and so there should be 2 unknowns. Okay, and sometimes it turns out that you get to a point in the recurrence relation that everything after that point is 0. And so what you get is a polynomial and not an infinite series. That's possible as well. Okay, so Frobenius's method is designed for the same thing. It's still a series method. It's still a series method. It is designed for differential equations with regular singular points. So with singular points that are regular, whatever that means. And it goes like this. And in fact, it's designed with x equals 0 as a regular singular point. Okay. So if you write it in standard form, so if there was something in front of the y double dash, you have to divide by it. You write in this form, a singular point is a point where one or both of these is undefined. Officially not analytic, but undefined will do the trick. And a regular singular point is one where if you multiply this by x and this, damn it, one of them by x and the other one by x squared, then they are defined. But I can never remember which one it is. So this one times x and this one times x squared. That makes sense. So singular 0 is a singular. I'm going to look it up. Give me a second. Frobenius's method is on page 57 of the notes. No, don't you dare. A regular singular point, x times this one and x squared times this one. Yep, that's what you said. So yeah, officially x minus x naught or squared. But if 0 wasn't a singular point, you'd do ordinary power series method, which is the one we just did. So there's no reason to do Frobenius's method when 0 isn't a singular point. Though to be fair, you could theoretically be asked to do it anyway, but yeah. So if 0 is a singular, x equals 0 is a singular point when p of 0 and or q of 0 are undefined. That's what we're gonna think of it as, but it's actually when p of x and or q of x are not analytic at x equals 0. That's the official version. But the one you think in your head is like, oh, they're undefined. Right, cool. They've got an x on the bottom, right? That's the problem. And so, but it's x equals 0 is a regular singular point when that happens, and also that x p of x and x squared q of x. You do that calculation and then notice that there are no x's on the bottom, basically. So are analytic, i.e. x's on bottom cancel out. No, if x wasn't singular at all, I'd use the normal method. If it means that one of these functions, when you put it into this format, is undefined. So the previous equation I had, when I divide by this, I don't get zeros in the denominator when I sub in x equals 0, basically. And so x isn't a singular point. X equals 0 isn't singular, so I can use the ordinary method. But if x equals 0 is singular, then you have to use Frobenius. And if it's not a regular singular point, then Frobenius's will not work. Then you're stuffed. Or you just, well, if 0 is an irregular singular point, then just pick a point that isn't regular and do all of this with x minus a instead of x.
Yeah.
I could go, oh, I'll pick 1, because 1 is a place where everything's defined, and I'll do all of this with an x minus 1 instead of an x. Yep. Yes. They're officially all about an expansion point. It's most common to do it with 0 because it's, yeah, you have to find a point where all the functions are defined. So yeah, if x is a singular point, is not a singular point, great. If x is a regular singular point, then Frobenius. So x equals 0, sorry. If x equals 0 is a singular point, great. Use this. If x equals 0 is, damn it. If x equals 0 is a singular point, but it's regular, use Frobenius. If x equals 0 is an irregular singular point, then go back to the beginning and use a different center. Use 1 instead or something. Yeah. Yeah, all of your sums will have x minus 1 to the m instead. But all the derivatives will be the same, and just everything will have an x minus 1.
Then you can get rid of that, still make some 0, but add or subtract the extra term.
Yeah, well, you don't have to add them, subtract the extra term at all. It doesn't make any difference. It's just that you'll be doing the coefficients of x minus 1 to the m. So it'll all be fine. It's just that when you use your initial boundary conditions, you'll be subbing in that point, subbing in x equals 1 instead of x equals 0. And so everything will just be, yeah. So it'll all actually work out exactly the same. It will not make any difference. I'm surprised that they don't get you to do the general Taylor series thing more often. But I mean, you get like one chance to practice each of these things, right? It'll be in each assignment, there's one. So that's why you keep asking me about it, because there's not enough practice. So Frobenius's method is extremely clever. It's saying, well, just a second, what if I had a Taylor series, but I just multiplied it by x to the power of like 2/3 or something? There'd be some other thing. So we're now going, so if x equals 0 is regular singular, is a regular singular point, try y equals x to the r for some unknown x to some unknown r, which may or may not be a whole number, and unknown a0, a1, etc. And what you're going to also do is you're going to assume that a0 isn't 0, because if it was, you'd just choose a bigger r. So if the first actual non-zero term was x cubed, you'd just choose your r to be 3 bigger. So we're going to assume a0 is not 0, because if it was, then you'd just choose a later r and it'll all work out anyway. All right. Whereas in this other one, in the traditional power series method, you do not assume anything about a0. It's allowed to be 0 in the traditional method, but in Frobenius's method, it's not allowed to be 0, the first a0. And that's all dealt with by finding the correct r. And so what you do is you rewrite this like this. Like that. You put this x to the r in here. And you do the same thing we did before. So you do everything the same. You do y dashed equals bleh. And in fact, this bit of the working is always identical. And you sub in and you do some index shifting. And you equate coefficients to 0. But at this point, when you start equating the coefficients to zero, that's when it starts to be different to the traditional method. Also, you will not, like in the other one, when you differentiated, you change this to a 1, but there's no telling if r is a whole number or not. And so there is no way of knowing if this is actually 0. So you definitely do not adjust the beginning point when you do the derivatives here, because you don't know for sure if it's going to be helpful or true. This is the point here where it starts to be different to ordinary series here. And that is because the earliest value of n that appears anywhere in any of your sums will tell you what r is. So I kind of have to do an example. I'll try and do a simple one, but yep. Just let me check that the recording is still happening. Yep, still happening. Because I'm recording through my computer, not through the lecture theatre, so the lecture theatre is not going to give up on me. So, that one. So this one, do I really want to do that? Yeah, I'm just going to leave it like that. So I should probably put an X somewhere. Let's do that. So this one, if I divide by that, standard form has y double dash plus 1 over x squared y dash minus 2 over x y. Both of those are undefined when x is 0. And so x equals 0 is a singular point. So 1 over x squared and minus 2 over x are not analytic. So in my head, I say undefined, but on the paper, I write not analytic. At x equals 0. So x equals 0 is a singular point, which means if it is a singular point, I'm not allowed to use the ordinary power series method. Because if it's a singular point, then my function won't have a Taylor series there. But x times 1 over, oh, is it x times this one? Damn it, there has to be an x in this one. Sorry. Sorry about that. Because you multiply the 1 with the y dash by x to make it into something that is not analytic. Can I just do, I'm just going to do it like this, if that's okay. Oh no, I'll leave it as an x. That's okay. Because you multiply this one by x and this one by x squared. And if there's it had an x squared on the bottom before, and if I multiply by x, it's still not defined because it's still 1 over x. So, but x times 1 over x equals 1, and minus 2 over x times x squared, which is minus 2x, are both analytic at x equals 0. So it's a regular singular point. Yeah. So the problem was before I had a 1 over x squared here, and 1 over x squared times x is 1 over x, which isn't analytic. Yeah. Yeah. That's right. So now it is I can use Frobenius. And I will assume that y is equal to m equals 0 to infinity a m x to the m plus r, with a naught not equal to 0. And y dashed is, I already wrote this down, but I'm going to have to do it again. So this bit of the working is always the same in every Frobenius method question. Thank you. Okay, and then I sub it in. Now I don't have so much work to do because none of these have two terms, so it won't be too hard. So x squared y double dashed is so multiplying by the x squared makes this -2 go up to a 0. And then x times y dashed, that's great. That's going to turn into something nice, isn't it? AM m plus r x m plus r -1 plus 1 because of the x. And minus 2xy, that's going to be bad. So the -2 times am and the x will be m plus r plus 1. So they're my three pieces. I'm going to have to shift this one. So I'm going to have to subtract 1 from here. And add 1 here. Okay, so now everything's lined up. So just know if this had been a -1, I could have added 1 here and subtracted 1 here and done an m equals -1. That's okay. It doesn't really matter. You can do it in whatever way you like. So now I'm going to say, have a look through all my three sums, these three sums. So we know that the total is 0 because this is my differential equation that I had originally, and it's supposed to work out to 0. So all right. When m equals the earliest m that appears in any of these three series is m equals 0. That's my earliest m. And it doesn't appear in all of the series. It doesn't appear in this one. But even if it did, I would still do the earliest m. And so the coefficient of x to the 0 plus r, coefficient of x to the 0 plus r when m equals 0, that's what I'm doing, will be a0 from the very top one here, a0, 0 plus r, 0 plus r minus 1. And this one's got an m equals 0, so that will give me an a0, 0 plus 1 here. And this one doesn't have an m equals 0, and so I won't use that one. Oh, 0 plus r, sorry, that's an r there, not a 1. I wrote that wrong earlier. And you know that a0 isn't 0, so I can divide by it. And now I get r outside of, sorry, what's that? Oh, r squared equals 0. That was unexpected. So r equals 0 or 0. Usually you get two different answers for r. And so what I will do, now that I know what r is, I will sub that in and see what happens. I'm mildly distressed that r equals 0 is an answer, but that's okay. So for r equals 0, and let me just do m is greater than 1. These are where all the m's are. Like now 1 occurs in all of these sums. This one's got 1, and these ones also have 1 because they started at 0. sometimes there's a second one that isn't in all the sums, and you have to do that one separately. But we haven't got that. M equals 1 is all of them, so I'm going to go for everything after that. I'll just do it in terms of m. And so I'm now going to have the coefficient of x to the m plus r, which is in fact x to the m. I'm mildly surprised that the r didn't work out. Like r equals 0 means that we can use an ordinary Taylor series, which is freaking me out. But anyway, it's okay. I guess it's just the p and the q that were undefined, not necessarily the y, maybe. Anyway, just freaking me out. So we've got m plus r minus 1. That's from this one. And m plus r from that one. And an am minus 1 times minus 2. Like that. And I know what m is. M is 0. But not m. I know what r is. R is 0. So I've got m minus 1 plus m minus 2 m minus 1 equals 0. And the traditional way of making a recurrence relation is to have the later value of m equals everything else. So I'm going to go am and so am. So I can factorize out the m and the am. I'm left with m minus 1 plus 1. Oh, yay. We knew that happened because it happened last time, didn't it? And so I've got am times m squared. And so am is 2 on m squared times am minus 1. And this doesn't start until m is 1. Which is good because I won't be dividing by 0. Okay, and this is the recurrence relation. And so we get that a0 is whatever it is. It's just not 0. And a1, according to this, will be 2 on 1 squared times a0, according to that. Usually they get you to do the first few. And this will be 2 on 2 squared a1, which is a half of a1, which when I sub in 2a0 into that gives me a0. And so on forever. But see, they've all got an a0 in them. And so we'll get y equals a0 x to the 0, like x to the 0 plus 0, plus a1. So I get x to the 0 because that's what r is. That's how the Frobenius method started. You'd have x to the r in this spot and then the Taylor series. And so we get 1 times a0 plus 2a0x plus a0x squared. And so that will be a0 times 1 plus 2x plus x squared plus, and there'll be more stuff there. And that's the best I can do. And that's probably good enough if x is close to 0. But you'll note I only got one solution. Officially, I've got a multiple of this solution. That's one of my independent solutions. If I then needed to find the other one, I need to then go back to the beginning and try something with like an ln in it or something. There's a rule for what you write down there in the notes somewhere. Yeah. No, we're finding the Taylor series via other methods, and then we are sure definitely that 2 is the derivative of x when the derivative of f when x is 0, and that 2 is also the derivative of, like, we now know what the derivatives are, for our function. So yeah, we didn't use any derivatives to find these coefficients. We found them by another method, and we could work backwards to find the derivatives from here. Yeah. Right. That, I think, will do. There is a way of dealing with it if you get so if you get two of the same R, then the other one will be the first one. So the other one should be this plus this times, no, I don't really understand it. There's a theorem SIG 5.8 for what to do to find the other solution, but I don't really get what to actually do at that point. I'm sorry. I hope I didn't go over into someone else's time. Yeah, so bear with me. I think you go to a whole other thing and then try to, and then sub it in from the beginning from scratch. So there's, at this stage, according to the notes, theorem 5.8, I will now try y equals this answer times ln, I don't know. I'm sorry, I don't understand it. It says that this would be y1. That's y1, and I'll try y2 is y1 times ln of x plus a new series. And I will not start at 0. I think you have to sub that in and see what you get. But I don't know. I don't think the lecturer has actually ever given any examples of what to do in those other situations. If you're really, really lucky, and this works out to be a polynomial because one of the later recurrence relations gives you a 0, then you can use reduction of order to find the other solution. Yeah. Yeah. That's why one up there in theorem 5.8 says that. I don't know. Not sure, basically. In general, at the Maths Learning Centre, I tend to only know things that are examinable or that I've had a chance to think about. So if it's not in, if the lecturer has said, I'm not going to assess this, then no one asks me at the Maths Learning Centre, so I don't know. Yeah, either things that I have done the later courses on, I know, or things that people have asked me about. So that's as far as it goes. And if you're very lucky, you actually get two different answers here, one with an A0 and one with an A1. If you're unlucky, you only get one, like we got here. If you're lucky, if you get two different R's, so we got two of the same R. If we got two different R's that were different by not a whole number, like not an integer, then hopefully that one of them will give you two solutions. And if it doesn't, the other one will give you a different solution. So you can try both R's and get two different answers. And if they're different by an integer, then you're stuffed and the same problem happens. Like if the two R's are different by an integer, then your two, so if you did them both, one is a multiple of the other. And so that's not helpful. Yeah, so there's just all these, give it a go, see what happens. Sometimes you get two solutions, sometimes you only get one, then you have to try something else. Yeah. I have seen the proof that two solutions that are different by an integer, for R that are different by an integer, will give you one solution is a multiple of the other, but I'm not sure I could reproduce it. So your lecturer didn't give you a proof of that either in your course. So if you haven't seen it, you don't have to. Yeah. I will say most of the equations they give you, the recurrence relation skips 2. Like see how this one is AM and AM minus 1? Usually it's like AM and AM minus 2. And so if it skips 2, then like this AM is found out from the previous one. Sometimes it's AM and AM minus 2. And so you can figure out A2 from A0 and A4 from A2. But A1 can't be figured out. And so you get it as A0 and A1. But today, because of the way I set it up, we went down by 1.
I think that's the
Mhm.
question. Or maps back to AM. That's
Yeah, it's more like if the two R's and an integer apart. That's the problem. So this isn't about the R's. So it's not a mistake. So what if you got AM is 2 on M squared A? Are you supposed to be using this room?
Yes.
Oh, sorry about that. You could have interrupted me at any moment.
Thank you.
I'll just stop. If it was this, that's okay. Oh, with an AM there, yeah, that would be bad. All right.